So let me start out by thanking the organizers for putting together this wonderful conference. I think it was really worth the wait. I have also listened carefully to the instructions that the review talks are not meant to showcase the work of the review speaker. And so I will not show any figures made by me or my immediate student, except in one case where I could not find a suitable alternative. I have also chosen to keep this introduction rather general, because I think it will be much better to hear all the details from those of you that actually did the work than to hear my poor summary of your work. And please forgive me if I did not mention your work in this review, either due to a lack of time or ignorance or oversight, but feel free to go to the Slack, add your comments, write a review of my review, add references, etc. So the summary of this talk, I think, is that we're finally able to select statistical samples of galaxy clusters in their early stages of formation, study their multi-wavelength properties. And this is extending classical research on clusters between the present day and cosmic noon well into the epoch of reionization, as I will show and other speakers will show this conference. Maybe not quite at the level of detail as provided by these wonderful hydro simulations of forming clusters, as in this example I show here, but maybe at a sufficient level of detail that we can start comparing data with theory and constrain the theory. So let me also try to summarize why I think we are all here. The story of cluster formation is the story of the history of the largest objects in the universe. And this is, of course, closely related to the cosmology. From a general galaxy formation standpoint, I think we're really missing important pieces of the puzzle if we only focus on field galaxies. Clusters contain large numbers of coeval galaxies that may have affected each other and their surroundings on length scales and time scales that are much larger than those for typical galaxies. And even if the physics that is happening in galaxies, in clusters and protoclusters may not be different than the physics that affects galaxy formation in general, there is at least a lot of unique astrophysics that is exclusively found in clusters and their progenitors. And then I'm thinking of galaxy evolution in dense environments, brightest cluster galaxies, the intercluster medium and the intercluster light, and also unique forms of AGN feedback and supermassive black holes. So I think this field is incredibly rich, and I like to see protoclusters as the time and place in history of the universe where all known aspects of galaxy formation are happening, as no doubt we will see during this week. From a theoretical perspective, we've known for quite some time that the more massive the dark matter halo, the earlier it formed its stars on average. This is a nice figure from the work of Beruzi et al. That I like to show. It shows you the mass evolution of dark matter halos. And this is color-coded by their star formation rates. So if you now focus on the progenitors of the most massive halos, then you see that their star formation really peaks at very high redshifts, certainly above redshift 2. And so that means that for massive clusters, most of the action happens at very high redshifts. And we also know this from an observational perspective based on galaxy clusters. The two examples I show here are probably not representative. They are rather extreme clusters at their respective redshifts of 1.2 and 1.8. The example by Ratura et al. 2010 shows you the derived stellar ages of the cluster ellipticals in CL1252 as a function of their stellar mass. And so for most of these cluster ellipticals, their stellar populations have ages very close to redshift of 4, 5, 6. And at the bottom, cluster at redshift 1.8, studied by Andrion et al., Newman et al., which is a remarkable object with a quiescent fraction of 80%, something like this. And so for these systems, we have missed all of the action that led to the formation of these systems. I think we all know that the classical cluster search techniques have limitations. These limitations limit our samples and selections to redshift 1.5 to 2 or so. These traditional searches are failing not only for technical reasons, right, X-ray sensitivities, etc., but also for astrophysical reasons. So the components of clusters that we are used to look for simply did not exist yet before these clusters became clusters. But it also translates into problems for establishing reliable mass proxies on which all of local cluster science is built. So think of the luminosity temperature relation, the Compton Y parameter, the richness class, or the velocity dispersion to get a virial mass. So most of this is becomes pretty, no disrespect, useless above redshift 2. Now, if we were to put on our dark matter glasses for a minute, then if we look up the sky, I think we would have no problem whatsoever to just point out where all the interesting structures are forming. And we can do this to very high redshifts, as you see here in this Millennium XXL simulation. At redshift 6, depending on the scale you're looking at, it will be very easy to point out where the progenitors of massive clusters are assembling. Now, unfortunately, we don't have such glasses, but mixed in with the dark matter, there will be gas and galaxies that we can detect. And so it really becomes a question of what should we be searching for, and whether our telescopes are big enough to detect these systems. I think it's important to talk about some basic definitions. None of these definitions are hills that I'm willing to die on. But I think we should make an attempt to agree on what we're talking about. So in this talk, when I say cluster, I'm thinking of virialized objects, single dark matter halos on a mass scale of at least 10 to the 14 solar masses, and then that defines a protocluster as the volume of space that will eventually collapse to form this object. And it must do this no later than redshift 0, okay, for us. Otherwise, it has little meaning to us. Now, this distinction between cluster protocols is only really practical in theory or simulations. As we all know, in the observations, the errors are significant on the mass estimates. This 10 to the 14 solar mass threshold is somewhat arbitrary, but I think it makes sense because the halo mass function is really steep at these high masses. So there's orders of magnitude more galaxy groups than there are 10 to the 14 solar mass clusters, and those are orders of magnitude more common than 10 to the 15 solar mass clusters. So some kind of mass distinction is important. An advantage of this definition is that then the total number density of clusters and protoclusters at any redshift will be equal to the cluster abundance today. But I'm well aware that there are other useful definitions possible and also being used by you. And for example, sensible questions to ask are, is there a thermalized X-ray ICM or not? Does the object have a well-defined red sequence? Or do we see the beginnings of strong environmental effects like RAM pressure? Now, we have known for quite some time that, at least from a theoretical perspective, we should have no problem of identifying these kind of structures before they virialized. And work from semi-analytic models principally has shown that we should be looking for giant beasts covering many co-moving physical megaparsecs in the sky. And we've also learned that the typical progenitor of a coma cluster first passes this 10 to the 14 solar mass cluster threshold at a redshift of about 2. Okay. lower mass clusters will typically pass this threshold much later, around redshift 1. Of course, the details between the different semitic models and the different hydro simulations differ, but in general, I think they all agree on these basic facts. And they also all agree on the fact that actually it seems that not only the selection of these systems is possible based on overdensities of galaxies or gas in the sky, but even estimates of the present-day masses are possible. So we know that higher mass clusters today generally came from larger overdensities. Searching for large overdensities of galaxies or gas selected in some way becomes cleaner if we look for larger overdensities, but they also become more incomplete. And simulations such as this figure from Lovell et al. 2018 shows that the overdensity measured at some redshift above 2, 3, 4, 5, etc. Actually is a reasonable proxy of the present-day cluster mass within its scatter. And so this means that in principle, we should be able to sort out evolutionary schemes for clusters and protoclusters by ordering the objects that we find in these ways. So 2 years ago, we made this rather simplistic overview of structures that have been found above redshift 2. I used to call them butterflies. But this figure was also made to actually highlight that that this field is going through a major acceleration, thanks largely due to large-scale projects, large-scale surveys that are now giving hundreds to thousands of candidate systems, of which I think many tens have been confirmed as cluster progenitors by now. It also means that spectroscopic follow-up has become one of the main limiting factors. So some of these ambitious projects that I'd like to highlight here are the following. So the first project is the Carlab project. Early work showed that protoclusters appeared in small but rather spectacular samples of high redshift radio galaxies. There's a review by Madi and De Broek 2008. And this was really taken to a next level by the Carlab project, led by Dominique Abdelzalek et al. It was a Spitzer survey of 400 powerful radio AGN at high redshift. And this really showed for the first time the statistical connection between radio AGN and galaxy overdensities, and has led to many confirmations since. It is still quite not clear to me, at least, what is so special about the radio AGN in particular that makes them these interesting probes of forming clusters. And maybe this is something we can discuss during this conference. So another game changer, I think, are the wide field deep optical surveys, such as the HyperSupremeChem program. In the work of Toshikawa et al. 2018, a sample was presented of 200 protoclusters or protocluster candidates at redshift 4, and about 75% of these should be genuine massive objects. They show a clustering signal that confirms this conclusion, and they're also detected in a deep stack of Planck data, showing that even though these objects are UV selected, they may harbor also large obscured star formation rates. And the work with the HyperSupremeChem imaging surveys being extended to other redshifts than redshift 4. Another huge surprise, I think, in recent years was the arrival of large blind spectroscopic surveys, such as the VMOS Ultradeep survey. These dense spectroscopic surveys, they allow us to find protoclusters where we didn't know they were, or where we weren't particularly looking. The example here of Olga Kuchiati et al. 2014 shows you that once you have a redshift of every object in a limited location on the sky, you can pick out the dense regions, even when the two-dimensional or the projected distribution of objects on the sky didn't allow you to identify these objects. Once you have all these spectra, you can stack them, and this opens interesting doors to study also the gas component of these systems, such as shown here on the right. And this is related to yet a whole new approach of finding these kind of systems through tomography of the intergalactic medium. And the example I'll show here from Carlab 2017 shows a massive structure of galaxies that was purely identified based on the absorption signal that they imprint on the spectra of quasars in the background. In the near future, I think we can expect this kind of surveys to really take off with instruments like VLT Moons and the Subaru Prime Spectrograph that will do massive multiplex surveys over very large sky areas for the first time in history. Another big surprise of recent years, I think, was the discovery of the so-called cold spots in CMB data, excesses of far infrared sub-millimeter objects. I highlight two objects that I think we'll hear a lot about this week, the so-called distant red core redshift 4 and the SPT2349 super coma progenitors, both at redshift 4. They offer also an interesting comparison to the UV selected systems. It seems we have IR bright and UV dark systems, and perhaps UV bright and IR bright or dark systems. Some of these show extremely compact structures that may signal the formation of a brightest cluster galaxy. And I also appreciate that some of the authors have started to make figures like here shown on the right from Long et al. 2020, where an initial attempt is being made to put the different structures in perspective and compare this to different accretion regimes we may expect as a function of mass and redshift. Some topics that keep coming back in the study of clusters, protoclusters, are topics such as the enhancement of the AGN fraction. We may expect that AGN are enhanced in protoclusters, for example, because faster galaxy growth leads to more massive galaxies, and more massive galaxies tend to be more frequently active. More frequent mergers may happen in overdense regions, or more efficient inflows of gas may trigger AGN. However, the data, I think, above redshift 2 does not yield a uniform picture yet. Yes, there are very interesting examples of protoclusters with that harbor many X-ray or radio-selected AGN, shown here on the left figure from Champagne et al. 2021. But if you put all the objects together in a plot, I think there's no consistent picture yet. I'm going to speed up a little bit. Another topic that keeps coming back in this protocluster business are the evidence for Lyman alpha blobs or halos or filaments. This seems to have some connection to dense environments that we don't quite understand yet, I think. And in the final few minutes, I want to take you all the way to the epoch of reionization, perhaps, and highlight that we are starting to find many examples of these protocluster systems at redshifts as high as 6, 7, 8. We can perhaps imagine that these would be major sources of the epoch of reionization due to their very high ionizing photon rates and large bias. Simulations indicate that several tens of % of the cosmic star formation rate density could actually be contributed by these large early forming systems. And so they may dominate the first maps of the neutral and the ionized IGM that we'll be able to make soon. Now, here are two examples of interesting Lyman alpha emitters from the EOR, late stage EOR, that show this double peaked Lyman alpha emission. And this is sort of the smoking gun of objects that are sitting in large ionized bubbles. The example on the left from Bosman et al. 2020 is actually a Lyman alpha emitter that sits in the ionization cone of a quasar at redshift 6. The object on the right by Mattei et al. Is a Lyman alpha emitter that probably sits in its own H2 blown large ionized region. And I think one of the ways in which we might be able to show whether these protoclusters are early reionized systems is if we can show that such profiles like these are common and actually in protoclusters. And actually they should be more common in protoclusters compared to field galaxies at the same redshift. So I think this will be one way in which we might be able to show this connection between protoclusters and the EOR. My last slide. Another topic I think that will come up today even are the complicated environments of the first quasars. I think theory tells us that these first quasars should form in the densest environments in the early universe. However, even though some spectacular examples exist, I would still argue that most current observations of these high redshift massive quasar systems do not support this important prediction from theory. There's many possibilities of what might be going on. Maybe we don't see the tracer galaxies, they're too faint or too dusty. Maybe the scales we're probing are too small. Maybe the quasars are forming in dense regions, but their photoionization delays star formation. Maybe the quasars are not in dense environments, or maybe it's something completely else. And I invite you to look at this paper by Weiss et al. That gives a very interesting idea that maybe the quasars need to form not in protoclusters, but near them, because they require a large background UV flux. This is my final slide. In past talks, I often have compared the study of protoclusters to butterfly collecting. I think we'll see many beautiful butterflies this week, and maybe we're finding enough that we can start doing some biology. But actually, it's even more complicated, given the many stages in the life of a butterfly that can look completely different. And I'll leave it to you to sort out which stages of the cluster and protocluster are the egg and the caterpillar and the butterfly. I guess so. These are the difficulties that we're facing in this field. Thank you very much.